Okay, picture this. You're standing right in front of a massive, load-bearing concrete pillar inside a 50-year-old building, and you need to know exactly how strong that concrete is right now, today, to make sure it's safe. Normally, the traditional direct method, well, you'd bring in heavy machinery, drill out a huge cylindrical core, lug it to a lab, and literally crush it to see when it fails. But what if you absolutely cannot afford to damage the structure? I mean, what if drilling a core actually weakens the very pillar you're trying to save? So how do you test a building's strength without breaking it? Well, welcome to this explainer. Today, we're unlocking the secrets of one of the most ingenious, non-destructive testing tools in structural engineering. It's called the Rebound Hammer. We're going to draw our insights directly from the official Indian Standard 13311, Part 2, which lays out the exact science of assessing existing concrete safely. We'll explore how a simple mechanical bounce can reveal the hidden strength of a massive building, look at the environmental traps that can absolutely ruin your data, and explain why this hammer needs a high-tech partner to truly get the job done. Here's our roadmap for today. First, we'll cover testing without breaking. Then we'll walk through the step-by-step procedure. After that, we'll look at dealing with outlying data, uncover the moisture content factor, and finally, wrap up with the UPV alliance. All right, let's jump right into Section 1, Testing Without Breaking. So our ultimate guide today is the official Indian Standard, put together by the Bureau of Indian Standards. You see, when you're making decisions that affect the structural integrity of a building and, frankly, public safety, you just can't rely on guesswork. You need a verified, standardized method. This document, IS 13311 Part 2, gives us the exact parameters for using the rebound hammer. It basically takes what could be a highly subjective guess and turns it into a rigorous, repeatable scientific process. So how does this actually work in practice? Well, it all comes down to a measurement called the rebound index. Inside the housing of a rebound hammer, there's a spring-controlled mass. When you press the plunger of the hammer against the surface of the concrete, that mass is released. It strikes the concrete and then bounces back. The rebound index is simply the graduated scale reading of exactly how far that mass rebounds. The principle here is brilliantly simple. The harder the surface of the concrete, the greater the rebound. And since surface hardness is fundamentally tied to the overall compressive strength of the concrete, we can use that bounce-back measurement to estimate just how strong the concrete really is. Now, this part is really cool because it shows that different structures need entirely different tools for the job. You can't just use one universal hammer for everything. Testing normal weight concrete, that requires an impact energy of roughly 2.25 Newton meters. But let's say you're testing lightweight concrete or maybe small impact-sensitive parts. You've got to drop that energy way down to 0.75. On the flip side, if you're out on a highway testing massive concrete pavements or heavy hydraulic structures, you're going to need a heavy-duty hammer delivering 30 Newton meters of impact energy. Matching the hammer's energy to your specific application is absolutely crucial. It's step 1 for getting accurate data. Moving on to Section 2, the step-by-step procedure. What's really fascinating here is just how tactile and precise this procedure actually is in the field. I mean, it's not just walking up and hitting a wall. First off, the surface has to be close-textured, smooth, clean, and dry. If there's any loosely adhering scale or rough spots left over from incomplete compaction, you literally have to take a grinding wheel or a stone and rub it off. Rough surfaces will give you totally unreliable results. Second, your point of impact has to be strictly maintained at least 20 millimeters away from any edge or shape discontinuity to prevent edge crushing. And third, the hammer must be held at perfect right angles to the concrete surface. You can test horizontally, vertically, upwards, downwards, but that 90-degree angle to the surface, that is non-negotiable if you want a valid reading. All right, Section 3, dealing with outlying data. That number right there, that is your golden rule, 6. When you're evaluating a specific point of observation on a concrete structure, engineers are strictly required to take exactly 6 readings of the rebound index around that area. Why? Well, concrete is a composite material, right? It's made of cement, sand, and large aggregate stones. So if your hammer happens to hit directly over a really hard piece of stone just beneath the surface, your reading is going to spike. If it hits a tiny hidden air void, it's going to plummet. Taking 6 readings is how you protect yourself from those random local variations. So the crucial takeaway is that this is all about cleaning the signal. You don't just take those 6 readings and blindly average them together. Doing that would pull your data toward any extreme spikes or dips. Instead, the standard demands that you identify and strictly delete outlying anomalous observations based on a separate standard, IS 8900-1978. That standard relies on strict statistical deviation thresholds. So only after you've thrown out the statistical outliers do you actually average the remaining consistent readings. And it's that cleaned, mathematically sound average that officially becomes your final rebound index for that specific point. Next up is Section 4, the moisture content factor. Now let's look at how moisture can totally trick the hammer. Say you have wet-cured concrete test specimens. You can't just pull them out of wet storage and test them right away. Nope, the standard requires them to be kept in the laboratory atmosphere to dry out for about 24 hours before testing. Attempting to directly correlate rebound numbers taken on a wet cube with the compressive strength of that wet cube is strictly not recommended. Water trapped inside the pores of the concrete fundamentally changes the surface hardness, which totally changes the resulting bounce. Similarly, you have to watch out for the surface finish itself. Troweled and floated surfaces artificially harden the outer layer. That'll cause the hammer to overestimate the actual strength of the concrete underneath. So you really have to know what it is you're heading. Which brings us to Section 5, the UPV Alliance. Okay, here is the fatal flaw of the rebound hammer if you try to use it entirely on its own. It is incredibly short-sighted. The rebound index is only indicative of compressive strength to a very limited depth from the surface. Think about it. If the concrete member looks perfectly hard on the outside, but has deep internal microcracking, hidden voids, or major structural inconsistencies across its cross-section, the rebound hammer is still going to bounce back beautifully and report a high strength. It remains completely blind to the actual internal reality of the structure. Because of this surface-level limitation, the standard is incredibly explicit. It states that it's preferable to use the rebound hammer in combination with ultrasonic pulse velocity, or UPV. Now, UPV is a dynamic test that sends high-frequency sound waves deep through the entire mass of the concrete. It measures exactly how fast those waves travel. Solid, dense concrete transmits sound very quickly, but cracked or honeycombed concrete, that slows the sound down. So UPV acts as this deep scanning diagnostician, making it the perfect and honestly necessary partner to the surface-level rebound hammer. Let's see how this builds into a strict conditional framework for engineers out in the field. The UPV test actually dictates whether you are even allowed to trust your rebound hammer data. It's basically a hierarchy. First, if you scan the concrete with UPV and the quality is assessed as excellent or good, you're clear to proceed. You can totally trust the rebound index to estimate the compressive strength. Second, if the UPV results are only medium, you can't rely solely on the hammer. You have to bring in collateral tests, like checking site cubes or doing limited core drilling to verify the numbers. And third, if the UPV test shows doubtful quality, meaning sound is moving sluggishly through a fractured interior, you must make absolutely no assessment of compressive strength from the rebound index. The standard strictly forbids it because the surface bounce is essentially lying about the internal decay. So what's the big takeaway from all this? The rebound hammer is a phenomenal, elegant tool for testing concrete without destroying it. By understanding the rigorous procedure behind it, managing your impact energies, cleaning the data of outliers, and controlling for things like moisture, we get a vital peek into the structural integrity of the buildings we use every single day. But as we've seen, it's really just one part of a larger diagnostic alliance, heavily reliant on the deep scanning power of ultrasonic pulse velocity. Which begs the question, if the rebound hammer is just our service-level specialist, what other non-destructive secrets are waiting in the engineer's toolkit to keep our world standing strong? Keep asking questions, keep looking beneath the surface, and thank you so much for joining me for this explainer.